Hey there, my name is Hannah Finney, and this is the second portion to my student project presentation for iterative processes and the onset of chaos. And there is the timestamp there. It's January 6th. It is 9:40. Oh, sorry about that. Um, Here's my name with my signature. And so we're going to be going over my establishment of the limit for if our iterative process was just a normal function, like the ones we've studied before. So I calculated that the limit of our function, assuming it was just a typical function, is equal to 1 over 3. And I had a fun time with the epsilon delta proof for this. And when I say I had a fun time, I wanted to bash my head into the wall after like 3 hours of trying to prove the limit of this function. So I think I finally figured out a way to do it, and I'll run through my whole process here. So I calculated the limit of our function in a couple of different ways. One of the ways that I calculated it is using the limit laws. So I separated the function into the product of two functions. So instead of f of x being equal to 1.5x minus 1.5x squared, I actually separated it into f of x being 1.5x and 1 minus x being g of x, I think I labeled it. So here I'm showing that you can calculate the same limit several different ways, but I wanted to show the product rule here. So when using the product rule, I get 1 over 3 as the value. And then I also have here the calculation using the sum difference rules. And that's where I have f of x being equal to 1.5x and g of x being equal to negative 1.5x squared. So we know that the limit of a additive function, or additive functions, when we are summing two functions and taking the limit, we can break that down into the limit of the first function plus the limit of the second function. So I broke those down here into the limit of 1.5x as x approached 1 over 3, and the limit of negative 1.5x squared as x approached 1 over 3. And the limit of 1.5x is the same thing, we can just plug and chug. I ended up with a value of 1 over 2, with the f of x being separate from g of x, and the limit of g of x being equal to negative 1 over 6 as x approaches 1 over 3. And then summing those two functions, we just have our same denominators here. I almost forgot the word denominator. Same denominators here. We get 4 over 12, which is equivalent to 1 over 3. So we can get the same results by using the sum laws, product laws, or just direct substitution. I did that as well, but didn't show it because that was my initial attempt at the epsilon delta proof. And I'm showing this before progressing into the epsilon delta proof, because I did end up proving using the epsilon delta proof to prove the limit of these functions separately instead of simply doing the epsilon delta proof for the function as a whole. Okay, so we know that if the limit of f of x is equal to L as x approaches a, and the limit of g of x is equal to m as x approaches a, then the limit of f of x plus g of x will be equal to the limit of L plus m, as I should have, that's a little typo right there, I should have as x approaches a. So I broke that down into what was demonstrated actually in our textbook as proof for the limit laws. Shown up here, which is that if f of x plus g of x minus L plus m, that the absolute value of that is the same thing as saying f of x minus L plus g of x minus m. The absolute value of that will be less than the absolute value of f of x minus L plus the absolute value of g of x minus m. And that will be less than epsilon over 2, which is important, plus epsilon over 2, which is equal to epsilon. So when we are solving for our delta value and we're looking for epsilon, I decided to break it down into those two functions and solve from there. So first we're going to assume that we have some epsilon value greater than 0. implying that we have a delta value greater than 0 such that 0 is less than the absolute value of x minus a, which is less than delta. And if that's the case, then we have the absolute value of our function f of x minus the limit of f of x is less than epsilon over 2, which is why I went through all of that previously. So here I am solving for an equivalent value for f of x minus L to be able to plug in our delta value. So here I have 3 over 2x minus 1 over 2. I end up factoring that out to solve for x minus 1 over 3, or x minus a, which is less than our delta value, and I end up with epsilon over 3. So, spoiler alert, we're going to choose our delta 1 value equal to epsilon over 3. And in the second part, we are going to repeat the process. So we're going to have some epsilon greater than 0 for our second function, g of x, and a delta 2 value greater than 0 such that 0 is less than x minus a, which is less than delta 2 for our g of x function, which implies that the absolute value of our g of x function minus m, which was the limit to our g of x function, will be less than epsilon over 2. And here we are factoring and solving for that value and end up coming down to a value of epsilon over the absolute value of 3x minus 1, which we will set equal to our second delta value. All right, so now we can finally prove it. So for our first function, we're going to set, let our epsilon be greater than 0. And we're going to choose a delta 1 value of epsilon over 3, implying that our x minus a is less than our delta 1 value, which is x minus 1 over 3, is less than delta 1. And here we're just doing all of our steps in reverse. So we can see that epsilon over 3 will be